And with that, it's my great honor to welcome Professor Chuchu Fan. Chuchu is now the associate professor in the Aeroastro department at MIT. Chuchu did a lot of great work in applying rigorous math into machine learning and AI to allow us to design, evaluate, fabricate, and verify those complex, intelligent, large-scale systems. And Chuchu has a lot of awards, including the Anessa Clear Award, the Ona Young Investigator Award, and the Oscar Young Investigator Award, among with many others. And today, Chuchu is going to share with us on her work on neural certificates. And without further ado, let's welcome Chuchu.
Thank you. Hey, great to see everyone. It's definitely quite a journey. Last time I gave a talk at CMU over Zoom. There was also some unexpected thing, which I didn't want to recall. But this one is a lot more fun. And I will try to speed up, so leave us some time and make sure the defense can happen on time. That's definitely more important. So very happy to be here to talk about some of our recent work. I call it neural certificates, but it's really an idea of how to blend rigorous mathematics into machine learning process. So when I talk about certificate functions, there are a couple of things in my mind. For lower level reliable control, we are very interested in this thing called control certificate functions. They are theoretical control tools people have developed for decades or even more than 100 years to guarantee certain properties of a system. Like the up-and-down function, if you took control, you pretty much know what it is. For barrier function, it's a very popular tool these days for guarantee safety. And there are many other similar versions of these for different types of properties. So why people love these control certificate functions? Because they are much easier to analyze. They would guarantee the properties like stability, safety of your system without asking you to solve the system dynamics. Instead, they are imposing inequality conditions. And although there has been a lot of work around certificate functions, it's still a difficult one to construct. So usually people need a lot of manual effort, or you need to be an expert to write down certain function for these systems. So the question we're interested in the past few years is how to learn control policies that we use the popular machine learning or reinforcement learning approaches, but we have this policy that come with a certificate function. And for higher level planning, the story is slightly different. So let's say, assume we have a reliable control policy that can control your robots to move from point A to point B. Still, there are many interesting questions. For example, in this one, I want to have an intelligent robot that's just going to do a very simple thing. The robot will need to get to its destination. However, there is a complicated maze and the keys is stored or hide somewhere. So the robot will need to figure out where the keys are. They need to grab the key, look at the number and see which corresponding door it can open. And there are many other constraints like timing constraints. There are definitely logical dependencies. And if I can think about a way similar to the certificate functions to describe these requirements, I can think of temporal logic. So if you're not familiar with temporal logic, that's totally okay. I'm going to give you a quick lecture of what it is, but it is a high-level specification language. It's not a control policy because temporal logic tells the robot what to do. It tells the robot the rules instead of how to do it. How to do it corresponds to the actions. So temporal logic, or in our work, we heavily rely on something called signal temporal logic. It can capture many complex planning considerations, specifically these logical dependencies. For example, you cannot travel through a door, you have to open it. To open it, you have to find a key, and you have to find the corresponding key to open it. And there are also temporal constraints, say you are only given a certain amount of time, or like this door, you get a passcode, it will expire in a certain amount of time. You have to plan accordingly. And more importantly, the reason we love temporal logic or signal temporal logic is that it can be translated from natural languages very easily. I'm not going to talk about how to do that translation. It's not about the talk today. And we have a bunch of work. Actually, on Sunday, there will be a workshop on foundation models for planning and control. I will talk about how to translate natural language into different type of specifications for control and planning. But the translated version will be this very concise, like mathematical formulation I wrote here. You can see that although it's short, it's actually precisely captured on my requirements. I have a color coding here, 3 pieces, and I have this symbolic way to represent what we want the robot to do. And now here, the question we're interested in is, can we develop a planner that can plan according to or satisfy the rules that are described in temporal logic? So in my talk today, I plan to separate it into 2 parts, not very balanced, maybe more heavily on the first part, but I do want to talk about this idea of blending rigorous mathematics like control certificate functions or temporal logic into your decision-making process. So now you have a policy or a planner that is learned, but the learned planner know exactly what it is doing, and it can guarantee you what it can do. So part 1, how do we learn control policies that come with certificate functions? If you have never heard about barrier function, I'm going to give you 2 slides to make a master of barrier function in 1 minute. Barrier function is a function that takes in the state information and environment and output a scalar value. This scalar value is going to be safe it's going to be positive for safe states, and it's going to be negative for unsafe states. Like I can control like a toy, a helicopter, it should avoid this dangerous volcano area. Why it's called a control barrier function is because it not only tell you safe from unsafe, it actually advises we can use it to compute what we call allowed input. In my toy example, the allowed input is allowed velocity, and everything below this bar is allowed in the corresponding location, so we can guarantee that your helicopter is safe. Of course, this single one is not going to contain everything if your scenario has changed, like I have another windy area. Now, I also want to avoid that windy area for the helicopter. I need a new CBF, again, positive for safe, negative for unsafe. And of course, the allowed input will change. Now, the question is, how can we get these blue and red bars quickly, even if the environment changes? So that's a question we're going to answer. So CBF, they're getting very popular these days, and many people have used it across many different applications. However, they are hard to be handcrafted or synthesized using classical methods like sum of squares for many systems, like systems that have nonlinear dynamics, have high-dimensional dynamics, or high-dimensional input, like a camera input, lidar input. If we have imprecise models or the model becomes unknown, when we have input constraints, we all know that our input threads, they have the actuators will have limits. We cannot assume arbitrary input, while the handcrafted CBF is going to be hard to consider these input constraints. Sometimes we have complex safety conditions that are not just distance, keep a good distance to the unsafe. It could be more complicated than the distance-based safety criteria. And in a multi-agent system, something we really care about is scale up. Can we develop a barrier function that can work for an arbitrary number of agents so that I don't have to come up with a new one whenever the scenario changes? So that's our considerations. And we know that the real world systems, they all fall into these categories. They are not linear systems or simple, double integrators. You can just handcraft a CBF. And this is also true for many other control certificates like the Aeronautics function, and even for decision-making like planning from signal temporal logic. All these are realistic considerations. So how can we blend the CBF again into our control and signal temporal logic into planning for systems that have these type of dynamics? I would say like my conclusion is something we call learning control certificates we have been working on for a while. It can be a very powerful tool to bridge this gap between model-based rigor and data-driven efficiency. So let me give you a specific example called graph control barrier function. This is a work that we developed 2 years ago for a distributed safe control with only local observations, and we consider input constraints. Let's see, we have an agent, multi-agent system, and these agents, they don't have to be the same. They can be heterogeneous. They could be an obstacle be an agent. I will give you a few examples. But if I have a multi-agent system, they are naturally a graph. And in my graph, I will have nodes, I have edge. For nodes, I can, to simplify a lot of things, I'm going to consider 2 types of nodes. One is an agent. The other one is whatever my LiDAR detected. So I don't care what that obstacle looks like. I only know that my LiDAR will have certain rays that spin around whatever that hit a surface or like an obstacle. It will tell me where the LiDAR hitting point is. Having those 2 nodes, I also now want to consider my edge. So I say that my robot has a limited sensing capability. It could be distance-based. It could be other type of sensing capability. You can define it, but there exists an edge whenever I can sense the other robot. For example, if the other one is close to me, or if the other agent, the LiDAR hitting ray is among the surface that my LiDAR can reach. So now to make it very rigorous, we say that every agent doesn't have to consider an arbitrary number of neighbors. There will be a finite number of agents that this ego agent, every agent as an ego agent has to consider, right? For example, if I have an agent here in the middle, that's a circular robot. It has a sensing radius of R, and I have other agents, they each occupy some space. Then in this case, there will be at most 6 of my neighbors. So including myself, I only have to consider 7 agents as like this small local observation. That's how we define local observation. Of course, in reality, we have to consider more. It is way more than 7, but there will be an upper number that we can use. And each of these LiDAR hitting array is also an agent that we consider. Now, having that, I'm ready to define my GCBF. If you have ever worked on CBF, GCBF is almost the same with every other CBF, but we do have a rigorous proof to show that this local version of the definition can give you a global safety certificate. So my GCBF is a continuously differentiable function H that will map this big X, which is the ego agent and all the neighboring information into a scalar value. Of course, it should follow the definition of CBF. I use my helicopter. It should be positive for safe, negative for unsafe. And the way it can advise a controller is through this inequality condition I have here in orange. What does this one says? It says, so first term says H dot, like forget about the second term. First term said H dot is positive. If H dot is positive, that means if my H is positive, that means safe. H dot is positive, that H can only increase. That's how I guarantee safety. But that's not ideal, because that means I have to stay away, further and further away from the boundary of safe and unsafe. That's not ideal. I might have to go to the boundary. I'll get close to the boundary to do something. That's why we have the second term here. The second term, alpha, is a class kappa function that is monotonically increasing and is 0 as 0. So whatever the form it is, as long as it's a class kappa function, it will guarantee that my agent is always safe within the safe boundary. If the closer it is to the safe boundary, there will be a kind of like a force to make it turn, but that's basically how how you can understand it. And this H dot term, we will have to consider its Lie derivative, which we will have to impose the dynamic information here. But so the original definition of a GCBF does have the dynamics, but later I will tell you how to get rid of it for the systems that you don't really have information about its dynamics. And one important thing we really need to impose to make GCBF valid is the following. We need the gradient of H with respect to other agents that are outside sensing radius to be 0. Basically, this Xj represents another neighbor agent J that is out my sensing radius, or that is something that the ego agent is not able to detect and has some distance to the eagle agent. We need that to be 0 for all the other agents. Now we can prove that the existence of a GCBF will guarantee the safety of an arbitrarily large multi-agent system. And of course, if you start from a non-colliding condition, the 0 super level set of H is going to be a control invariant set, which means my system will stay for the safe distance with each other. Now, having that, how do I make sure like this gradient term is going to be 0 for all the agents that I don't have to care about? And this can be naturally realized if you work on graph neural networks. The graph attention layer might be able to capture what I mean. Now, have that. The way we are going to learn GCBF is going to parameterize both the GCBF function H and my policy pi as graph neural networks. And I'm going to just jointly, this is the first approach to get a GCBF. If you have the dynamics information, we can use this lost term to do backpropagation and find my H and policy pi for the system, where the lost function has 3 terms. The 3 terms are also super easy. So the EI here is the input feature to the GNN, which include both node and edge features. Now, what are the node features? You can design different types of my agent. It could be, all the friend neighbors or friend agents to be type 1, your LiDAR hitting rate to be type 2, the adversary agents to be type 3. You can define your node feature. And for the edge feature, we can talk about the distance or whatever information your neighboring agent want to share with you. And this will be aggregated into this input feature Z. Now, I just need first term, the derivative of H plus that alpha function is going to be positive. And for the states that are unsafe, H is negative. For the states that are safe or control invariant, we want them to be positive. So that's as easy as it is. And it turns out if we learn them as GNNs, we see that this plot here, the x-axis is the distance to the other agents, and the y-axis is the attention weight. And remember, we want this derivative partial derivative with respect to agents that are outside my sensing radius to be 0. You can see how the attention weight is going to not monotonically decreasing and become 0 when it's outside the sensing radius. So having that, now if I'm giving a multi-agent system where I'm only plotting 3 so we can see it, these blue agents try to navigate to their destination. Destination are plotted in green, and they can talk to each other, or they can communicate when they have a distance that's close, or they don't really talk to each other when they're further away, and they have this spinning LiDAR arrays to detect where the other obstacles are. Now, behind the scene, what I'm plotting is the GCBF in the eye of this agent with a star. So in the eye of that agent, you can see we have the GCBF plotted there. That's the behind the scene reason for all these agents being able to navigate to their destination safely. So this GCBF in learning, in this case, supervised learning, we see that it can make the resulting controller explainable. Sorry, something I forgot to mention here is we are actually plotting the attention weights here. So the attention weights is the width of this edge here. So the thicker it is, it means the attention weight is bigger. And we can see that it's exactly capturing what we want. Let me play this again. This video is a little bit laggy, but the line becomes much thicker when it detects the neighboring agent that's close. And the more it's further away, the line becomes thinner on the right-hand side. So this can really explain why the controller is making that decision. It's looking at its all neighboring edges and calculate the weighted sum and decide where to move. The closer that neighboring agent is, the calculated controller will make it to move to a direction that avoid direct collision to that agent. And it's more than explainable. This can make our multi-agent controller scalable and generalizable. So we trained with 8 agents because we assume there will be only at most 7 neighbors around me. And the resulting controller really can be deployed theoretically on an arbitrary number of agents of the same dynamics. Of course, if your dynamics change, you need to just get another copy of that controller for your different types of the dynamics. On the right-hand side here, I have up to more than 200, but in the paper, we have done experiments for more than 4,000, and the safety rate is perfectly like 100% if I keep the density of the environment roughly the same. But of course, I can make it denser and denser. In that case, at some point, it's like so crowded, the agents will not be able to move. And you can see the safety rate is pretty high, but the reach rate, the basic agents cannot reach their destination on time. And it can be trained without the explicit models of the obstacles, because we only care about that LiDAR hitting rays, LiDAR hitting points. In training, we just randomly sample these hitting points. Now they can avoid different types of obstacles that can move around, they have different shapes. We can do this zero-shot transfer to hardware, like for example, we have different type of experiments. Everything is trained in simulation directly deployed on hardware. We have this robots switching their docking platform, or we have the formation swap when there is an adversarial agent. We can have other type of obstacles and some sort of inspection job. All these videos, we can see, for example, on the right top one, there is an adversarial agent actually controlled by a human and trying to poke, like get close to a lot of the agents. And we can see their job is to switch their position, but they can also avoid the other obstacles nicely. And the bottom one here, it's two surveillance robots, surveillance drones trying to move around the circle and always monitor this moving spot, but it cannot bump to the spot. You can see like they two are required to stay close, and they also have to avoid this moving spot that is randomly move around. And we have a more interesting inspection job later. So that is a quick introduction of GCBF in supervised learning. Now, when we study the GCBF, we find this is an interesting idea to guarantee safety. And safety, the reason it is difficult is because it's often considered as a competing objective with my performance. If I take a step back and look at general optimal control problems, my general optimal control problem will be formulated as I have an objective I want to optimize against. And I also need to satisfy some task specifications like safety or even higher level requirements. And of course, my system will have to satisfy the unknown dynamics. The system dynamics, sometimes they can be unknown. I have a few examples like these are going to be more difficult. So previously, when my multi-agent systems are moving around, their objectives is very simple. They just have a goal. They have to reach there. But now I could have an airplane that's traveling through a very narrow corridor, but the performance is to safely travel through there and keep a very low altitude. Why? If you watch Top Gun 2, that's why. I have a drone that's delivering packages within the city, but the city could have wind, and there's the wind distribution will be different. Now the drone may have some, dilemmas. It could fly against the strong wind, but it may be delayed, or the battery may run out. But it could take a longer route, which you can make use of the wind. So your objective is to minimize the battery consumption. And some inspection robot, the performance, the objective here is to make sure that object that is being monitored is always, tracked, is always something that you can see. You don't want to lose that object. So if I turn this into an optimal control framework, I'm going to do a multi-agent because it's, if I can make multi-agent work, the single agent should naturally follow. It's similar to the following mathematical problem. I want this policy to be distributed. So if it's not going to be distributed, I will have to face this problem of scaling up later on. So if I could get a distributed policy that can minimize a global cost, the reason is because now my agents may have some joint task they have to do together. Like I know their manufacturing is really a big topic here. A lot of the manufacturing robots, they have to work collaboratively to finish one task. So there's one global objective, but I want my agents to have a distributed policy and they all stay safe. So for staying safety, I assume that my safety conditions can be described as this inequality, just to move it closer to the definition of CBF. But it can be quite general. For each agent, if I can write down my safety conditions as some sort of function of H over my observations to be positive, that would be good enough. And the agents, I assume it only has local observations, doesn't really know the entire environment. It can only see what's around. It can only receive what others want to share with them. And the policy is, of course, made by this use this local observation. And finally, this the dynamics could be unknown. If I have all this together, this is a standard multi-agent safe optimal control problem. How would we solve it normally? If I don't have the safety requirements, I can just use some sort of a multi-agent RL policy or other approaches that you like to get it. However, when there is a constraint, a set of constraints, what people normally do is to use Lagrangian duality or some similar form of it. I have to flip this hard constraint to a soft constraint, and I will have to optimize against this Lagrangian duality form. Now, when we do that, we will have at least two objectives, if not more. And as we said, in many cases, safety is against performance. The best way to keep safe is to stay still. You don't move. Then in many cases, it's going to be safe. But do not move means you're not making progress to your task. In this case, the consequence is that we are constantly optimizing against two competing objectives. I have to be really careful with that weight. If I penalize too much on violation of safety, my system may stay safe, but the performance is really poor. Otherwise, it may just ignore my safety constraints. Now, can we use the idea of GCBF to tackle this issue here in hard constrained safe optimal control problem? I have already talked about, local observation, not a problem. GCBF is able to handle it. And agents staying safe, the format looks like something a barrier function would use. So looks like GCBF should be able to help here. So how does it help? In GCBF, I do assume two things. The first is there is already a known policy that gets to my agent to the destination. So there's a green bubble or green dot. My agent knows how to get to the green dot. So I know a original policy. Here, I don't have that. And the second is I have a known continuous dynamics that I was using in defining GCBF. So how do I get rid of number 1 and number 4 so I can make GCBF part of the optimal control problem? The first part is unknown dynamics. If I don't have dynamics, what is a GCBF? How could I define it? The key insight here is something that we proved, a constraint value function, VH, which I'm going to calculate it by taking the minimum of H over the infinite horizon. So H is your safety safety constraint. If I take the minimum of H over infinite horizon, and if I can get this constraint value function, it itself is a legit control barrier function for my system if it's a single agent. And if it's a multi-agent system with partial observability, it is also a legit GCBF for a multi-agent system. So I'm going to be very happy with this observation. So here I'm plotting this VH for the 3-agent scenario. You can see that this is not GCBF. This is the value of V of H, taking the minimum of H. You can see it looks almost like a GCBF that I presented before. And theoretically, we can also prove it. Now, the issue with number 4 is solved. What we are going to do is we're going to run some sort of agent policy and collect the rollouts, which have to be deterministic rollouts, and use this deterministic rollouts to calculate my constraint value function. So that's one part of my algorithm. Now, if I do not really consider safety, as I said, this is a standard multi-agent optimal control problem. I can run some sort of a multi-agent RL algorithm to solve for it. A standard one could be MAPPO, where I'm still running this policy, collect my stochastic rollouts, and use that standard approach to optimize against my value function correspond to my objective. So that is a standard MAPPO framework. How do I blend these two things together? That is something called DGPPO, discrete graph PPO. So I have my standard MAPPO. What I'm going to do is to blend these two things together using something called gradient projection. So the way it works is also quite easy. Now, instead of doing the standard gradient step, I'm going to do a gradient projection. So my constraint value function, VH here, it is a GCBF. It is kind of like working as a filter that is looking at if my current gradient is taking the right step. If my current policy is safe according to my GCBF, then the gradient is taking a step towards optimizing my objective. Otherwise, it will be projected to make sure I'm taking a step towards a safer policy. Okay, so the gradient projection here is really the key to connect these two different value functions together. And if I put it together, that's basically the entire framework. And of course, one immediate complaint people could have is you have to collect the more simulation trajectories. You have to have the stochastic rollouts. You have to have the deterministic rollouts. You are doubling the samples. And the short answer is yes, we do need more rollouts than the standard MAPPO method. But there is something we could do. We can actually kind of, you reuse the stochastic rollouts by just taking the zero, take the mean and use it as some set of the rollouts for both the training. And so the entire framework looks like this. Now, as a result, this CBF or GCBF can be naturally blended into the RL process or MARL process. You don't have to use MAPPO. You can use any multi-agent RL policy algorithm that you like. Now, the good part of it is safety is no longer compromised when I use Lagrangian methods. It is going to be a hard constraint. However, among all the policies that give me a safe result, this is still achieving the optimal policy. Of course, up to whatever the MAPPO algorithm can solve. There will be tasks that are too difficult for MAPPO. There are some simple tasks like now, instead of going to the destination, I can ask my agents to form a line or I think over there to cover all the goals. Or they together push a box to make sure the center of the box is not going to collide with other obstacles. Or, these are some standard MARL benchmarks that people have used, I'd say 2 years ago. If I look at the numerical results, remember what we want to achieve is safety as a hard constraint, and at the same time, I want to optimize my cost. So x-axis here is the cost, y is the safety rate. Now, where is DGPPO? It is right here at the left top corner. It is not always giving us the best cost, but among all the cost that is low, it gave us the best safety rate. Among all the policies that are safe, we have the best cost. So it can really achieve the best of the two worlds. Compare with other approaches, like we either simply use the penalty-based approach or use Lagrangian, you can see that these two approaches, they will have to make a trade-off. If we penalize the safety too much, the performance will start to drop, give you a high cost. And if I don't penalize my safety, then the safety rate is going to drop. But there will be more interesting tasks we can do here. Now, coming back to my motivating examples. Here, we can drive this 16-dimensional fixed-wing airplane instead of asking Maverick, who, according to the movie, is the only person who can do that task. Of course, at some point, he led 2 trainees to do it. But we have a always safe auto Maverick who can drive the airplane to travel through a very narrow corridor only with LiDAR. So those green lights are the LiDAR points and keep a low altitude. Here is another standard task I would say that a lot of multi-agent people would use is there's a narrow gate. I have a bunch of agents. They have to travel through the narrow gate but they cannot all get through it together. We are not telling them the order. They're just figuring out the best way to do it themselves. Another interesting task I want to mention here is this inspection robot. Now, there are a couple of objectives and also safety considerations. I have one target drone that is moving around, and I have two control drone. I want to use my DGPPO algorithm. Now, what the drone have is each drone is carrying a camera, and the drone wants to just see the camera, see the target within its range, which is this, this triangle gray range. If the target move out of it, then it cannot be really seen. Objective is to maximize the time that the target is seen. When the target is seen, it is shown in green, and if it is not seen, it is going to be shown by yellow. There will be safety considerations. First of all, I have some keep out zone. Basically, in front of the target and behind the target are areas I do not want the inspection robots to get close to. Otherwise, it might be too dangerous. We do not really control the target. If the target accelerates, they may bump to each other. So the inspection robot will have to see from the two sides, and there will be static obstacles. So running DGPPO, and again, when they're too far away, they're not really talking to each other. But the policies learn that now when one robot's view is blocked by the obstacles, the other one come to pick it up, take over the observation task, and keep monitoring the target. And you can see how they are seamlessly taking over the job from one to another and make sure this target is always green, meaning it's always being observed. Okay, so that is a story I want to share about GCBF. Of course, there are still a lot to be explored. Even just the multi-agent reinforcement learning algorithm itself has a lot of things that we can improve, so we can take on more complicated tasks. But I do want to spend just a few minutes to tell you how we can level up. Now, say we have a reliable safe controller that can do certain low-level tasks like getting us from point A to point B, and optimizing some objectives like keep tracking of a target or other things that we have talked about. Now, at a higher level, can we get a planner that can also give us higher level plans that consider these timing constraints or logical dependencies? So my part 2 is about how to learn a planner that can also satisfy the STL specifications or general arbitrary STL specifications. And I'm going to show you that idea of doing this with GCBF is actually quite similar. We're basically using a very similar architecture to represent both. So what is STL? STL, if you have never heard about temporal logic, don't worry. I'm not going to give you another lecture of temporal logic today. It just so you know, it provides a mathematical framework for specifying complex robot behaviors with precise timing and logical constraints. It has a couple of interesting things we could use. It talk about temporal operators. It can talk about goal condition, like eventually you have to finish something, or you have to always, keep safe, always keep a battery not low. It have these logical things of until, like you cannot do something until you have finished your previous task. It also have these precise time intervals to tell you the exact time you want every task to happen. And it has logical operators like the normal ones, and or not, and other implication, etc., the ones you would use. And it comes with something called the robustness score. For every behavior of your system and for every STL, it can give you a single value, very much like CBF, right? It will be positive if your system satisfies STL and negative if it is not satisfied. So in that sense, it's actually quite similar to a GCBF. It has many applications, like self-driving. People have studied this a lot. In fact, Toyota folks proved that every single traffic rule can be expressed in signal temporal logic. And many robotics people, circuit design people, they are using this using temporal logic. I have a few cute applications that we have done previously. For example, like finding the key. So in this one, you can see that the robot is moving around, find the corresponding key, and open the red door and get to the destination. In the middle there, it's some sort of self-driving cars learning about the traffic light rule. So every intersection is either a stop sign or a traffic light, and the robots learn to look at the different crossing and satisfying the corresponding rule. Like at a stop sign, you have to first stop and observe the other vehicles, wait for your turn, and then pass by. And you can also do it for collaborative tasks like manufacturing. Why do we need temporal logic here? All these pieces, they have a specific order to be put together. So certain piece cannot be there until the supporting piece comes in. Sometimes you have to glue two things, so that comes with timing constraints. So there are lots of interesting applications, but planning from temporal logic or STL itself, it is a very difficult problem. People have shown that synthesizing trajectories that satisfy general STL for general dynamics is an NP-hard problem. So there's, the scalability issue that we have to deal with. And the people have done a lot of work in this domain. I won't have time to cover everything, but I would classify them into two big clusters of approaches. The first one is classical approaches that either using gradient descent or using sampling-based approach or using automata-based approach, mixed integer-based approach. They are pretty powerful in terms of giving you a satisfying solution, but they are extremely slow. For example, if I use any of this approach to find a trajectory that can solve the puzzle of finding the key and open the door, it usually takes minutes and hours just to solve a very small piece of puzzle. Not to say for like this assembly job, it would take hours to find a satisfying solution. There are also learning-based approaches like either supervised learning or reinforcement learning. They're actually a very broad literature here. The problem there is they can only handle fixed signal temporal logic, which means you are given a rule and you have to find a policy that satisfies the rule. Whatever part of that rule changes, you have to do this all over again. It takes hours or sometimes days to find a new policy. So that's also not ideal. I cannot stop my car there and spend a day so it can learn how to travel through a traffic light. Now, our goal is to be able to find a planner that can take in an STL formula and directly give you a trajectory that satisfies it. So we wanted to be able to handle general rules. And the way we're going to do it is going to follow 3 steps. First, we're going to embed an STL as a graph, like our multi-agent system. And we're going to use GN encoding. Not surprising, we have been working on GN for a while. So we are going to use GN to extract meaningful embeddings from this STL syntax. And finally, we're going to use flow matching to make sure we can match from the STL GN representation embedding to the specific trajectory. Now, to give you an example, if say I have this rule where it says you eventually either go to 1 or go to 2, but you cannot go to 3. You can pick one of them to join. So this one, if I write it as a STL formula here, what I'm going to do next is to have a graph encoding where each of this node is going to be either a operator type, like the temporal operator or the logical operator, or the time window, or the object coordinates, or whatever information I have about this system. Taking this graph encoding here, we'll use a GNN encoder together with information of the entire state, like where your obstacles are, where your destination is, together into a flow matching process. And flow, if you haven't worked on it before, is actually a quite powerful tool that was developed about 3 years ago as a general version of a diffusion model to generate as a generative model. In this case, we are using it as a generative model for trajectories. Okay, now that's basically the idea. Now, the similarity here shares a lot of similarity with the GCBF approach. So now we are showing that even if you have a higher level of a specification, not just the simple safety, it can still be embedded as a graph neural network. Its robustness works very similar to the GCBF, and we can use flow matching to find not only just an action, but trajectories. So here we have done some experiments that are going to be considering the higher level planning tasks. So to be able to get any sort of a generative model, we need to collect data set. So we indeed collected 200,000 diverse specifications, as like hopefully they can cover a wide range of different STLs people would use. Of course, it's not going to cover everything. I'm not confident to say that it can do any arbitrary STL, but reasonable STL with reasonable length are pretty much covered. Each of them are paired with trajectory demonstrations we collected using the solvers, either the gradient-based solvers or the sampling-based solvers. And the data set spans over different dynamics, like the Dubin cars or some environments that people who work on majorcal environments care about, the maze or the ant maze or manipulator tasks. And if you care about what's the training time for it, if I use just a single standard GPU, it takes between 8 to 24 hours, depending on the size of your data set, to have this flow model. So as a result, so there are lots of numbers here. I'm not going to go through everything, but in general, it can achieve quite a few improvements. We can get a very good speed up. Remember, the classical solvers, the problem is they are very slow at solving these temporal logic tasks. We achieve more than 100 times speed up and also efficiency with pretty high success rate. Okay, so I think I am doing a good job in terms of keeping things on time. Let me just summarize what I have talked about. We have talked about two types of neural certificates. One is control certificate. For example, today we learned about GCBF, and there are many other certificates like Lyapunov functions, contraction metric, etc. And even neural specifications, higher level specifications, they can be encoded, embedded as a neural representation and seamlessly blended into the machine learning process in both supervised learning and reinforcement learning. And we believe that it can serve to bridge the gap between the model-based rigor that people really care about when you're working on safety critical systems with data-driven efficiency, especially for the challenging systems. Now, GCBF and the STL encoding can handle nonlinear and high-dimensional dynamics. It can do unknown dynamics if we use the reinforcement learning version of it. It can consider input constraints. Sorry, I didn't really talk about the details of there, but we are able to incorporate the input constraints into the process. And safety conditions now is much more broad than just the distance-based safety. We can scale up to an arbitrary number of agents. I do want to say that there are limitations of this work. The first or the obvious limitation is, although I call them certificate functions or formal specifications, we cannot provide a formal guarantee for this whatever thing we have learned, either the certificate functions or the policies, because they are learned as a neural network representation. I cannot guarantee them. It's a hard work. I always say that I leave this hard work to my friends who work on neural network verifications. I want to say that formal verification, if anyone knew my history, I was a formal verification person, and the problem was like so hard, and I finished my PhD, I gave up. It's so hard because for these particular systems, it's computationally intractable. They're often undecidable. So if I want to perform exact formal verification, if I'm looking at this type of systems, this problem itself become undecidable, meaning I cannot even come up with an algorithm. Of course, I can do approximations or I can do, like over approximations or some probabilistic guarantees, but those I will have to make trade-off between verifiability and scalability. So far, our work has tried to push the direction of scalability, generalizability, how to generalize across different dynamics, different specifications. But in the future, we do need some sort of approach. Most likely, I think it will be a hybrid approach that will be able to take into the verification part and provide some guarantees. And I look very much forward to ideas about how we can do that. So with that, let me conclude my talk. And I do want to acknowledge all the good work that done by the three folks and many other people here. So my students, Songyuan and Oswin, they have been heavily working on GCBF and multi-agent RL. They have a lot of good work. If you want to look at what the state of the art, safe multi-agent RL, you can check out their work. And Yue is another student who mostly work on the higher level specification and STL-based planning. He's going to graduate 1 week from now. Next week at this time, I will be sitting in his defense. congratulate him, and he's going to join Apple as a research scientist to see if we can blend STL into the general generative models. And I have a QR code that can go to our group website. But whatever I've talked about today, they're all described there. With that, let me pause here. Sorry, I didn't take any questions, but now I think we have some time for the questions.
Thank you, Chuchu, for this great talk. Let's do questions until 3:29, and then we need to leave this room. Okay.
Hey, thanks for the great talk. I was wondering, so the way CBFs works when you deploy them online typically is you check if there's an action that satisfies some inequality constraint. I was wondering, how often does that inequality constraint become infeasible? Like when is there no action that satisfies that, and what do you do about that?
That's a good question. So basically, traditionally, how CBF works is you construct the CBF and you use it to solve a quadratic programming. And you have to find a feasible solution to that quadratic program. That's why this input constraint comes as a problem, because if the system has an input constraint, the quadratic programming may return a result that doesn't really satisfy this input constraint, and you don't really actually have a safe policy. Now here in the stuff I have shown, we are directly using the policies that are jointly learned. So we are not solving that quadratic programming. So in the first work, let me get back here. So in the first supervised learning here, we actually have a pi that is learned as a GNN, and we're directly testing the performance of that GNN, and safety rate is very high. In RL, here there is the RL, sorry, let me come back to this point. There is an action that is, the agent policy that is learned. We're directly looking at the policy. So not solving the QP, but you do, that basically means we learn the policy that comes with the barrier function, but we're not using the barrier function. It's kind of like throw away the barrier function. They're more of like guiding the learning process. But in other work, we have shown that you can use this barrier function as a safety filter. You can use it on top of other policies that you care about. And in that case, you do potentially could have the issue that, this quadratic program is going to be infeasible. I think that is going to be a hard problem. We'll also need some sort of verification to show within, the feasible set of this quadratic program is going to be large enough. In our work, where the title is quite easy to remember, it's called How to Train a Neural CBF. So if you look at that paper, we talk about how to train a neural CBF that can give you a maximum control invariant set. And if you have the control invariant set, within the control invariant set, you do have the feasible solution. But the best we can do is to give you a big enough control invariant set. Yeah.
Thank you for the great talk. I had a quick question about the STL.
Yeah.
So from the presentation, it seemed like you have tried to, or you have used it to provide specifications for the task. And I was wondering if you've also looked at using STL to provide some kind of prior information. For instance, for manufacturing assembly task, like assembly instructions are available. I wonder if that's something that you know.
Yeah, absolutely. So STL can capture any formal specifications that consider logical timing and other type of, first order logic constraints. And so I wouldn't have time to talk about it here, but in our other line of work where we are connecting LLM with as LLM agentic work, where we are using STL as one part of the intermediate language, where LLM can translate to it, and LLM can fill out the background information, like in the assembly work, because all the common knowledge, everything we will describe in the same form of intermediate language, and this language will be given to a formal planner to give you the plan.
Thank you.
Yep. First, I really appreciate the great talk.
Thanks.
And I have simple two questions. The first one is about the STL. You mentioned at the beginning of the presentation. As I understand that you said STL is not to let the drone, like robots or agents, not to do actions, but give them rules.
Yeah.
How to do. Yeah. So is there any also approach, like give them rule not to do? Like, yeah.
not to do the.
Yeah. I mean, like, for example, in humankind, we easily can think about the example of like, don't go to such area, like, don't do like something, yeah, so is there such approach also exist in the research? And second one is that, SPO seems like it's easily, apply, and like, it seems really easy to apply some, very hot topic like vision language models, so
Yeah.
like large language models, so is there any approach recently to, yeah?
Yeah, so for the first question, let me get back to my toy example. So something not to do in STL would be just negation, like do not travel across the wall.
Yeah.
Is just a negation, like not wall, and you have to always satisfy it. I say like if you know what not to do, you can incorporate it as part of STL. But if you don't know what you are not supposed to do, it will be hard. Like as this is a specification language. It's not common knowledge that people use. So if you know all the information about what you should do and what should not do, they can all be incorporated as part of STL. So the negation is a powerful thing, just to say not this, right? Negation basically means no this. And your second question is, has anyone incorporate STL as part of the Gen AI tools like LLM or
Yeah,
tools?
because it's really like human friendly, yeah.
Yeah. So I would say there are some initial work. So people love STLs because this connects better to what people think in as rules than some black box model that can give you an action. A lot of people I know in the car companies, not really generative AI methods, but in car companies they have studied for a very long time how to incorporate traffic rules and other design rules. In circuit design, they have been using temporal logic as part of the standard. Actually, temporal logic itself is part of the IEEE standard for circuit design. I know most of you do not work on circuits, but if you use like Synopsys or these EDA tools, you need to know temporal logic is part of the language there. I think how to incorporate that into Gen AI is going to be an interesting task. We have done some initial work to connect all the formal planners with LLMs. So LLM will, instead of planning by itself, it will translate everything into temporal logic, call a planner, look at the results, and reason over the result and see whether LLM improve the planning success rate of the LLMs. So I'll be talking about that on Sunday if you plan to attend that workshop.
Yeah, that workshop happens in Sheraton Hotel. People downtown.
Okay.
Yeah, with that, I would like to thank Chuchu again. Yeah, thank you.